Hello, welcome to the today class. Today we'll talk about ray tracing. These are the today class objectives. We will talk about overall algorithm of recursive ray tracing. Along that line, we'll talk about how we can perform how we can generate rays. Also, we'll talk about how we can perform the intersection test between ray and the geometry of the 3D models. These topics will be covered in the part 2 of my book, especially the chapter 10. Also, the last time we talked about how we can utilize the concept of texture mapping for adding the details for the geometry, also the light. So along that line, we talked about environment mapping, also this bump mapping and other techniques. So basically, the ray casting, ray tracing, which are the related techniques. These are techniques. The ray casting actually they're one of the example of this visibility algorithm. So visibility algorithm is nothing but given the set of this triangle, we want to identify what are the visible triangle. So in this case, we can see the triangle of this triangle but not the triangle of this cube, which is located behind of this cone. So in the case of the rasterization, we use this G buffering, right? So G buffering is nothing but we had some sort of this 2D map that containing the depth value, and by comparing this G value, depth value, we can very easily know that which one is the behind, which one is more close to us. Today we will talk about another this visibility algorithm known as the ray casting, and then if we recursively perform this ray casting, then we can design this ray tracing technique. So ray casting is very simple algorithm. So here this is actually our viewpoint. This is actually image plane, and here are actually the 2D illustration of our scene. You can treat that as a triangle, and for each pixel we generate ray. In this case, nothing there, so we just return this background color. And then next pixel, we also generate another ray from the origin passing through the center of this pixel point, and then we find the closest object along that ray, and then we can also evaluate, and then we compute the color. So we can also utilizing this phone illumination. We can compute at that cases at the intersection point. We can utilize we can evaluate the ambient, diffuse, also the specular tone or the phone illumination. And then we keep doing that. For other one, we do that. So we got the red color. And for this one, this ray actually intersects with this blue triangle, so we got the blue color, and we keep doing that. So it seems like conceptually, it seems very similar to the G buffering. But there are fundamental differences. So one of the main advantages of ray casting is that it's conceptually simple, right? I mean, we just generate ray passing through each pixel, and then we detect this intersection point, and we actually then we compute color, right? But in the case of the G buffering, in the case of rasterization, basically it is much more involved, right? We need to talk about how we can project this triangle into this image space, and what are the projection metrics, and then how we can do this visibility test using the depth value, right? So basically, the ray casting is kind of conceptually simple. Also, it can be very easily extended to handle other global illumination effect, which I will talk about later on. But it actually has some of the major disadvantages. One is that the renderer, in this case ray tracing technique, the rendering engine must have access to the entire retained mode. Basically, retained mode is nothing but entire data structure. So we should have all the data structure in the main memory. So think about it. In the case of rasterization, we just take the one triangle, we project into image space, and we do the rasterization, right? When we're doing that process, we don't need to access all the other rest of triangle, right? So basically, in the case of rasterization, we just access triangle one by one. That's the main benefit. In other words, the amount of the data that we have to access is very small. But in the case of ray casting, also the ray tracing, so given this ray, in this case, we actually this ray intersects with this triangle, right? This one for that ray, we also intersect with this triangle. But for the neighboring pixel, in this case, also we suddenly intersected with this blue triangle. on the next one will suddenly intersect with another this green triangle. You can see that first way we can actually basically we might access the totally different triangle, right? So as a result, we have to maintain all those data structure in the main memory, and then we have to randomly accessing those data of the distributed model. So in terms of the memory access pattern, rasterization is much better, right? We sequentially access this data, but in the case of raycasting, we kind of randomly accessing those ones. So as we try to access data in a random way, obviously it takes a lot of time. It takes a lot of time in terms of fetching the data to the disk, to the memory, and so on. So that's one of the main issue. Also, it was a little bit hard to map hard to design the specially designed hardware for ray tracing. As you can see, it's randomly accessing data. So early on, you require this branch prediction and other ones. But on the other hand, rasterization case, it was much simpler, right? We just sequentially traverse the triangle and we project triangle one by one to the image space, and we do the rasterization within the image space, which is actually, it turns out that it's very simple. Also, we can design those algorithms in a dedicated hardware known as the GPU. But it has been much more difficult to design the special hardware for ray tracing. As a result, the ray tracing was not adopted early on for rendering 3D models. So basically, as I mentioned before, the raycasting, raycasting was dismissed early on due to the aforementioned problem. But around 1980, Turner Whitted actually showed this image and then gained popularity again. So basically, if you look at basically Turner Whitted applied the raycasting and ray tracing to support this kind of the rendering effect. As you can see that this texture mapping, also shadow going on here, this shadow effect. Also, there are this transparent sphere. You can see that basically highlight, and then there's refraction. You can see this flow refracted on the surface of this glass and many other effects. So it showed actually potentials of the ray tracing for supporting the global illumination. And since then, the ray tracing has been studied again. So basically, these are the general idea of the raycasting, ray tracing. So basically, the raycasting and ray tracing nothing but just using the raycasting in a recursive way. So we trace ray from the eye into the scene. So basically, this is backward ray tracing. Let me show the Y. Actually, this is showing the basic algorithm of ray tracing. This is our eye, and this is actually image plane. There are 3D models. We generate ray. This is actually primary ray. We generate primary ray from the eye to pass through the center of each pixel, and so on. And basically, as you can see, this is a kind of the similarity between this raycasting and ray tracing algorithm with the physical simulation, physical interaction between light and material. As you can see, suppose that there are light here, then the light emitting photons, right? And then photons photons actually the light emit the photon in all over the direction, and some of photons are hitting here and they're reflected from the material, and then it may actually bounce into that direction, passing in that direction and reaching into our eye, right? As you can see, the ray tracing actually starting to do this simulation in a reverse way. In other words, we treat the photon actually emitting from our eye and passing through the center and so on, right? So the raycasting, ray tracing actually mimicking the physical interaction between light and material, but in a reverse way. That's why I would say that basically this is actually the backward ray tracing. We trace ray from the eye into the 3D scene, and raycasting actually used to compute visibility at the eye, as we seen from here. And then we do perform the ray tracing, which is nothing but recursive performing of the raycasting, recursive ray tracing for arbitrary ray needed for the differentiating. So we can support the refraction, also this transparency. So basically, this indicates some of the materials actually the transparent, like the glass window, and also we can support the shadows. We can generate ray for supporting this kind of effect. So here I show the basic algorithm of ray tracing, generating primary ray from the RI to the scene. And if there's intersection between ray and 3D model, we transfer the color at the intersection point to that pixel. This is a primary ray. As you can see, this just you can see that this is conceptually same to the project rasterization process, projecting this triangle on top of the image space. But we are not doing that. Instead, we generating ray from the here to the 3D scene. And if we wanted to support the shadow, suppose that we generate primary ray from here by passing through this pixel, and we are reaching here, right? And then if we wanted to support basically we want to support the shadow here. If there's some region, say in the shadow region of this object, it looks dark, right? On the other region, it looks bright, right? And how do you know that at the case of ray tracing? At that intersection point with the primary ray and the scene, if you want to support if you want to know whether this region is in the shadow region or not, we generate another ray. Here we set the secondary ray. We generate secondary shadow ray from the intersection point to the light. And then as you can see along that line, along that ray, there's an intersection between some other object and this ray, right? And at that case, it means that we cannot get the some light energy from the light source to here. So that at that case, we only evaluate ambient term, and then we only show the ambient energy to the pixel. But for other region, at the let's say this region, here actually we generate primary ray here, and then we also generate secondary shadow ray from here to the light source, and then we can reach the light source, right? And then it means that we can receive the energy, so that we evaluate ambient or diffuse and send that information, send that color to that pixel. And then depending and then depending on the material type of this one, we can also generate some other ray. So this shadow. And now let's talk about this reflection. So here, as you can, so this cylinder, cylinder shaped objects, it's like mirror light. So you reflect this other image on the surface of this cylinder. So how can you do that? We also again generate primary ray, and then if it hit with this reflective material, then suppose in this case we assume that this is actually a perfect mirror. Then this incoming ray, and then on that point, on that intersection point, we can also know the normal vector, right? And then if this perfect specular model, then we can apply the Snell's law, assuming that incoming and outgoing angle actually same thing, right? So that actually we can compute this reflection ray. So we only talk about at the case of specular material. We talked about how we can compute this R vector given this incoming viewing vector of the normal vector. We can apply that machinery from there to here. And so at the case object specular, this is the case, and then we cast secondary reflection ray from hit point and then to that direction. And then here we got the intersection, right? And then we can actually transfer. We can compute we also evaluate ambient diffuse term here. We get the color, and then we transfer the color to here, also that pixel. That way we can see this scene on the surface of this metallic object. So as you can see, the last time we talked about texture mapping, right? Do you remember what kind of the map to support? What kind of map we use for supporting this kind of reflection? We talked about the environment mapping, right? There has been we can use the environment map. Also, there are some issues of using environment map, right? But in the case of this ray tracing, we can just very simply generating another ray, in this case reflection ray, and we can support this reflection. As you can see, it's very simple, right? So that's the main beauty of the ray tracing. But here, in the case of in the case of rasterization, if you want to support certain effect, we need to create some maps, right? To the maps of texture, right? But in the case of this ray tracing, if you want to support certain effect, we just generate another ray. That's the main differentiation between the concept of the rasterization and also this ray tracing. Now let's talk about this refraction. I mean, if the objects are transparent, I mean, suppose that we treat that this actual glass, then we can cast the secondary refracted ray, right? But in the case of the rasterization, I even did not talk about how we can support this refraction, right? How we can support this transparent object. It is very complicated, but there are tons of paper of using some sort of the texture map for supporting this refraction. But in the case of the actual ray tracing, I can very easily explain this concept. So here we also generate primary ray, and then we hit it there, and then this object intersects with this ray. It's suppose that this material is transparent. Then we also generate another secondary ray. This we say this refraction ray. Again, also using using the Snell's law. So in this case, this glass might have its own material property. In this case, it might have a different refractive index. So by using again the Snell's law with the different refractive index, we can compute this refracted ray, and then we actually hitting the another surface of glass, and then also we again apply this Snell's law with the different refractive index. We can reaching here. Then we passing the color, arriving at the floor, and then passing the color to here to there, and then at the pixel. So that actually we can see through some other region of this texture map under this transparent object. So again, in the case of the ray tracing, we just generate ray for supporting effect. As you can see, we can actually generate a lot of ray to support the different kinds of this effect. Now let me talk about illumination model. So basically, before we talked about phone illumination model. If you look at this equation, this ambient term, diffuse term, specular term, right? But actually, this term fitted illumination model that are actually used for with this ray tracing. Basically, the technique that used for generating this model. It's kind of old, but let me briefly talk about some of the main ideas here. So again, for the visible light, we evaluate ambient, diffuse, but here we have some new terms here. Here SNT. SNT is nothing but SNT intensity of light from the reflection. S is for the reflection ray, and then T is the transmission ray. If the sum of the objects actually there is mirror-like object, we generate a reflection ray, right? And then we do that, and then we got the color from that reflection ray, and we adding that light intensity to the other terms here. And in case of S is actually the specular coefficient depending on the material type. And same thing KT for the transparent object. So again, we generate the ray. In this case, we didn't generate ray, right? For the specular term, we actually apply the phone illumination model so that we can support somehow the non-ideal specular appearance. But here, we actually generate additional ray for supporting this mirror-like object, also this transparent object. I grabbed this figure from the original paper. It looks complicated, but basically this is the incoming ray. This is viewing v vector, this viewing direction incoming ray, and this normal. And then according to if we assume that it's perfect mirror, then we can compute this reflection vector so that we can generate reflection ray from here to that direction. And then if we got some color up there, we adding that color to there actually. At that point, we evaluate the ambient diffuse here if it's visible, and then also for the reflection ray, we got some other colors, and we adding that color to the here, and send the summation of that color to that pixel. And if the model also this glass-like transparent model, we're also generating this transmission. The transparent, basically this is talk about this transmission or the transparent, also this refraction. So in this case, we generate refraction ray for that direction. And then for the reflection, these ones also can be described by Snell's law. If you want to know the exact definition of if you want to know how we can compute these ray, I recommend you to look at my book where I have actually described the detailed description for how to generate those rays. Okay, so let me briefly summarize what we need to do for rendering this 3D model with the ray tracing. Given this pixel, we generate primary ray here, and then we intersect it here, right? And then this model is actually this model has the specular material. We also generate reflection ray from here to that direction, right? And then also if we want to generate, if you want to support shadow, then we also generate another second ray from here to the shadow here. If we got the light energy, we can also we also actually accumulate light energy from the light source. And then for the reflection ray, we generate here, and then also intersect there. And then also we can also support another reflection here. Also another reflection ray in that direction. Also we will generate another shadow ray. And then here also this property has, if some of the material has also the transparent property, I mean same material can have the different property like the specular property, like the reflecting something. Also there some of the, if you look at the glass, I mean basically if you look at the glass, you can see that some of the light energy actually reflected on the surface of glass. Also you can see through some other the portion of this glass, right? So that actually then we will generate refraction ray here, and then also we can also generate another shadow ray, and then we also penetrate object, and then we keep doing that until it ends up with the light source. So as you can see, for performing the ray tracing, we need to generate a lot of ray. Also as you can see, it requires a lot of the computations. Also as you can see, for processing this ray, you require it actually to access the 3D data in almost a random way. As a result, it takes a lot of cache misses, and then it requires the very fast I/O computation. It requires very fast fetching from the data from the disk to the main memory, or main memory to the chip, the CPU and GPU. So right now, but the recent GPU actually evolved a lot to support this kind of the process. Now actually recent GPU can support this ray tracing techniques. Also here we can also visualize how the ray actually generated. Here actually we start from the I primary ray, and then depending on the material, and then if this ray is there, and then if we want to support the reflection, we generate reflection ray and shadow ray or transmission ray, and then we keep doing that in a recursive way. So actually, you're also visualizing this how the ray actually generated in a different directions. This overall structure, overall algorithm of ray tracing. First pixel, we compute the ray, let's say R, and then we perform the ray tracing. This is actually the functional ray tracing. We call the ray tracing function with this ray. And then we need to first compute the intersection between this ray and against the object. If there's no heating, then we return the background color. Otherwise, at that hit point, we need to evaluate the shading. In other words, we need to compute the ambient diffuse term, and then depending on your material type, we actually generate another secondary ray R prime. After generate secondary ray R prime if necessary. And then we need to also handle that ray, right? So that's why we recursively call this function with this new secondary ray R prime, and then we might get the color again, right? Let's say C prime, the light energy, and then we adding the C prime to C, and then we actually use this light energy for that pixel. That's the general structure of the ray tracing. So far I talked about overall algorithm of ray tracing. Now I'd like to talk about the more low-level details here. First of all, you can see that to perform ray tracing, we need to have we are using ray a lot. So I'd like to talk about ray representation. So the ray is basically we can define the ray with each origin. In this case, we usually for the case of primary ray, it starts from our eye, right? So this is actually eye position. And then we can also define the ray direction. Then any point on that direction can be represented by this parameter representation as a function of t. So we starting from the origin, and then we can represent any point on the ray with this formulation. And then based on this ray representation, we can also do the intersection, which I will talk about later on. So there, again, this is our eye. Let's say this indicating our image space, and then this let's say this is actually indicating center of each pixel. And for that, here 1 pixel here, we actually another ray passes through the center of this pixel, and there will be another pixel, and we also generate another ray, primary ray passing through the center of that one. We keep doing that. And for the general secondary ray, in this case, actually, its origin usually in the intersection point of the primary ray. For example, here for the primary ray, here, if we want to support the second shadow ray, this will be this intersection point of the primary ray. We treat it as the origin for that secondary ray, and then we also compute the direction from here to that light source. We generate the direction of secondary ray. That this is what it indicates. The origin is intersection point of primary ray typically, and direction depends on the type of ray. Shadow ray, we use the direction to the light source, and then reflection ray, we use the incoming direction of the normal to compute the reflection directions. Also, this transparency, or we can call this refraction ray, we use the Snell's law. Then, based on that, we can compute it. And once we generate ray, then we need to perform the intersection point. And given a ray, we need to compute what are the visible triangle, right? So we need to perform the intersection test between every single triangle of the scene and then this ray, right? And then we need to find what's the closest hit point to the viewer. But that's actually visible point to the viewer. So the general strategy is that we need to actually perform the intersection test between a ray and then mathematical description of the object. Then the question is what's the mathematical description of the object? Here actually I will just talk about the simple strategy. Typically, we only talk about the parameter ray equation as a function of t, right? This equation just describes all the point along the ray as a function of the parameter t, right? And then for the ray trace, we typically assume to use the implicit surface equation as shown here. Basically, this actually object representation. Basically, it describes all the point on the surface. And if you plug that point onto that function, it gives the 0, right? So all the points satisfying this equation are on the surface of the model. And then if we plug this ray equation into this implicit surface equation, then we can get this one, right? And then we solve this equation as a function of the t. Then we can compute once we know the t, then if we plug the value of the t over there, then we can know what are the intersection point. Then I will talk about this concept in a concrete example. Here, we just assume that all the objects are represented by the plane. Then this is actually implicit equation of the plane. You can see that you can recall when you talked about the education. For the rasterization, we talked about this one, right? We used this equation. This is normal, also the d, and in the case of the normal, it's actually of the plane is a unit vector. Then this that gives the distance from the origin to the plane, right? So here actually we have certain plane. Then we plug the ray equation into that implicit equation. Then we got this one. Then we formulated this equation. Like this, then we can know the certain t value. So basically, all the information is actually given already. Then we plug the value over there, we can get this t value. Then if obviously t value should be the positive, right? If the negative, it means that the ray actually intersecting the behind. Then we ignore that kind of negative case. So then we can, if there are multiple planes, we actually perform all the ray plane intersection tests, and out of there we might have multiple t value, and then we pick the smallest t value. Then that's the actually visible point to that ray. Okay, so far I talked about the overall the algorithm of the recursive ray tracing. The ray tracing generally indicating it's the recursive structure. So we typically call just the ray tracing. And then if we want to support the different effect, we just generate ray. And then we need to perform the intersection test between ray and object. For that case, we typically use these implicit equations. And then if you want to know details about some of the components, I recommend you to go over chapter 10 of the ray tracing of my book. And next time, as you can see, there are a lot of rays, and if there are a lot of the triangle, then basically performing ray tracing takes a lot of time. So we will talk about the acceleration data structure, and then we will talk about how to extend the Bayes ray tracing algorithm to support many other advanced rendering effects. This general homework, go over the next lecture slide before taking the class, and submit the question 2 times during the whole semester. So basically, there will be only one more class. So if you haven't submitted the question, please do so. For this lecture, also coming the last lecture, then you can satisfy the requirement for the homework. Okay, that's it. Thanks so much. Bye.